Hi everyone, and welcome to my presentation for the ICLA 2020 workshop on scene understanding and semantic SLAM. Today I want to describe our ongoing effort going from SLAM to real-time high-level understanding. My name is Luca Carlone, and I'm an assistant professor at MIT. I'm also the director of the Spark Lab at MIT. My lab is working in the broad area of robotics and autonomous systems, and in particular we focus on perception and computer vision for robotics. We have three big research topics we are pushing on in our lab, and I'm listing these in this slide. So we have a lot of ongoing effort on robust perception and algorithms for localization and mapping that are capable of working in extreme conditions. So I suggest you to check out our line of work on certifiable algorithms, including past work on visual inertial navigation and ongoing work on LiDAR-based LAM. The second line of work is on high-level scene understanding and what a number of people in the community are calling spatial AI. And this includes most of the topics I'm going to cover today. So recent contribution along this line include Chimera, which is an ICLA 2020 paper, and 3D dynamic scene graph, which will be presented at RSS next month. A third line of research is a little bit tangential to perception and is about computation, communication, co-design in processing networks, as well as other research topics dealing with embodied intelligence and, for example, soft manipulation for UAVs. So today I'm going to mostly cover the topic in the middle here about high-level scene understanding because it's the most relevant for the workshop. And the plan is for me to cover two basic contributions. The first one is Chimera, which is an effort to go from SLAM to metric semantic mapping. And the second one is 3D dynamic scene graphs, which is attempting to go from metric semantic mapping to high-level understanding. These are both contributions led by my student Tony, as well as other students in Spark, including Marcus, Arjun, Yoon, and Jingnan. So we start with Chimera. And my initial slide is just a reminder that as a community, we should be proud of the accomplishment we made in SLAM over the last several years. Right now, we have algorithms and implementation, including OrbSLAM and DSO, which are able to produce a sparse or semi-dense point cloud map of the environment in real time, and also more recent contributions, such as Ultimate SLAM, which are capable of pushing the boundary of agile camera motion by using advanced sensors, such as event-based cameras. This progress on the research side has been steadily transitioning into products. For example, the SkyDR1 drone is using visual inertial navigation technology to perform localization and mapping, and virtual and augmented reality technologies such as the Oculus Rift goggles and Pokemon Go are using algorithms for visual inertial navigation and visual SLAM, and other efforts are pushing the boundary of algorithms and hardware for SLAM, including startups such as Artisans or SLAM Core, or on-chip implementations such as the Navy on-chip. While we should be proud of the accomplishment we made in the context of SLAM, sometimes it's also useful to put things into perspective. And I think that a good exercise to do that is to compare the state of the art in robot perception against a very good perception system, which we're very familiar with, which is human perception. So on one side, if you look at robot perception, our SLAM algorithms are getting very good at obtaining a sparse or dense point cloud representation of the environment. And pioneering work, including SLAM++, are able to get object-level maps of the environment. In general, there are a number of works also trying to estimate other geometric primitives, including lines, voxels, and meshes. However, if you think about human perception, it turns out that humans are able to do much more than geometry. Just see for yourself. If as a human you stare at this image for a few seconds, you definitely realize the geometry of the scene. You realize that there is a street here, but you also understand the semantics of the scene. You can distinguish cars from pedestrians and so on. You can understand that yellow cars are essentially taxis. You can understand relation among the different objects. For example, the car is behind the other. And you can also kind of reason on the scene at different level of abstraction. So you can think about objects such as cars, you can think about the road, you can think about cities, and you can abstract away the content of the image. And you can do all these just by looking at a single image. So this is pretty far from what you are capable of doing with a robot. And what I want to stress is that this is not just an intellectual pursuit. The goal of bridging robot perception and human perception is not just an intellectual pursuit, but it's something that can essentially enhance the type of robotics product and robotics deployment we can enable. So for example, if I'm thinking about robotics right now, most of the commands we issue to our robots are in terms of coordinates. You know, the robot has to reach location XYZ on a map, for example. However, if I think about a robot I would like to interact with in the future, I would like to issue high-level commands to this robot. For example, go and pick up a cup of coffee. And this requires the robot to have advanced high-level understanding of the environment. So, of course, the lack of this high-level understanding is limiting application in robotics and application involving human-robot interactions, but is also like, a limiting factor on a number of other domains, including self-driving vehicles. For example, the fact that the car is not understanding the scene is potentially a safety risk for the car itself, and is limiting application like virtual and augmented reality. So to understand the potential of having a robot really understanding at high level the scene it is looking at, I'm picturing in my mind something like Alexa, and imagine a future Alexa which has a deep high-level understanding of the environment. To such Alexa, I would be able to ask, Alexa, where did I leave my coffee mug? And this future Alexa will be able to answer that I left it on the table near the window in the dining room, because Alexa would have this sophisticated understanding of objects and their spatial location. Of course, this is out of reach for current algorithms. Probably like Alexa will have no idea about my Mac, or will have no idea about the spatial layout of my house. So over the last 3 years, we've been pushing on this idea of bridging the gap between robot perception and human perception. And the first substantial step we took towards this goal is to design Chimera, which is a real-time metric semantic simultaneous localization and mapping library. So the input to Chimera is a set of images as the one that you can get from a camera, and IMU measurements from an inertial measurement unit. So these kind of inputs are the one produced by standard camera, for example, the Intel RealSense. And the output of Chimera is something that you can watch in this video, is essentially a 3D model in the form of a 3D mesh, in which the mesh not only describes the scene in 3D, but also comes with semantic annotations. So each phase of the mesh comes in a different color, which correspond to a different semantic label. So for example, ground here is in gray, walls are in green, and if we keep going, there will be desks in yellow, chairs in green, and so on. So this is the kind of metric semantic mapping capabilities that Chimera is able to achieve. So in the next few slides, I'm going to give you like a few insights about what we use in Chimera to get this kind of output. But I also want to point out that actually we have an open source and very good online implementation of Chimera, so you can just check it out for details. So Chimera is, at the core, is including 3 main building blocks. The first block is Chimera VIO, which is a tool for visual inertial odometry, and includes also a mesher for mesh reconstruction. The second one is Chimera Robust Post-Graph Optimization. And the last one is Chimera Semantics. And I will try to give you some insight about each module in the next few slides. So Chimera VIO is a state-of-the-art, real-time robust visual inertial odometry implementation, and is based on the IMU pre-integration work we proposed a while back. So what the IMU pre-integration work does is essentially to enable an optimization-based approach for visual inertial odometry, which is not only very accurate because it's optimization-based, but it's also very fast. And we can get keyframe poses at more than 20 Hertz, and we can get state estimates between keyframe at more than 100 Hertz. So it's real-time and it's very fast. Besides being real-time, Chimera VIO is also robust, and there is an outlier robust approach for feature tracking, which is based on our previous work on structureless projection factors. So the result of Chimera VIO is what you see in this video. Essentially, by using visual inertial data, Chimera VIO is able to reconstruct the trajectory of the robot over time in a completely unknown environment. It's able to reconstruct the points, which are essentially the 3D landmarks used in the VIO. And on top of that is also to reconstruct a local mesh of the environment in a matter of milliseconds. The second module in Chimera is the post-graph optimization. So in post-graph optimization, what Chimera does is to build a post-graph describing essentially the trajectory of the robot over time, starting from the initial pose of the robot to the current location, and including potentially loop closures, which are shown in blue here in this image. So the way we look for loop closures in Chimera is pretty standard, just by using a bag-of-words approach based on orbit descriptors. What is more sophisticated is the way in which we reject bad loop closure. We reject outliers. And this is based on the pairwise consistency maximization approach proposed by Mendelssohn et al. In 2018, for which we implement essentially an incremental version that can operate in real time on a common laptop. And the impact of using this outlier rejection is pretty evident from this slide. On the left, you see what happens to the trajectory estimate of the robot if you do not do outlier rejection for bad loop closure. Even without knowing the ground truth trajectory, you can see that this trajectory is very messy because we are accepting bad loop closures. On the other hand, if you use the proposed outlier rejection approach, we still have few good loop closures, which are shown in blue here. But the trajectory is very nice and smooth because essentially we're rejecting bad loop closures. Once you have this globally consistent reconstruction of the trajectory, we can use Chimera semantics to get a complete and global metric semantic mesh reconstruction. So the geometric part of it, the metric 3D reconstruction, is based on a volumetric grid approach, which is VoxBlocks, is a very good implementation from ETH. On top of that, what we do is to add the semantics. In a nutshell, for the semantics, what we do is to take a 2D pixel-wise segmentation of each image, which is something that you can get using a standard deep neural network. And we back project this 2D segmentation into 3D using ray tracing and using Bayesian updates to fuse information over multiple images. And this is the kind of result that we get. So it's a mesh which is dense and is semantically labeled. Something that I want to mention is that this idea of labeling geometric models in 3D is something that showed up also in, for example, semantic fusion and fusion++. Something that is very unique of this work is that we are doing everything on CPU. So we have a very fast implementation, which does not require a GPU. And for just the mapping side of it can run faster than 10 Hertz on a standard CPU and a standard laptop. So besides looking at the qualitative results, we also have top performance on the quantitative side. In the paper of Chimera, you can find the evaluation of each module. Here I'm showing just few details about the performance of Chimera VIO and the postgraph optimization Chimera PGO. So what you can see here is a table showing the errors on the Europe datasets. So on the rows of the table, you see the different Europe datasets. And on the columns, you can see the different techniques we compared, including fixed leg smoothing techniques, full smoothing techniques, and approaches including loop closure. And in boldface, you see the corresponding entry getting the smallest error, so the best performing approach. And you can see that Chimera is essentially outperforming the state of the art, both when applied in a fixed leg smoothing setup, in a full smoothing setup, and even with loop closure. It is worth mentioning that switching from fixed leg smoothing to full smoothing is a single parameter in Chimera, which you can just adjust using the YAML file, the parameters in input to Chimera. In the paper, of course, we have evaluation of the 3D reconstruction and the semantic reconstruction in Chimera. Here, I just have the time to show you qualitative results comparing the type of mesh that we can get out of Chimera with the ground truth mesh, which in this case is available in a photorealistic simulation. So Chimera is a very modular library. The message here is that each module is achieving state-of-the-art performance, and you can use the module that you care the most about. Either you use Chimera as an entire library, or for example, you just take the visual inertial odometry part. While working on Chimera, I think was a good step towards getting to a high-level understanding and bridging essentially robot perception to human perception. We realized that metric semantic mapping is not the end goal here. So the second contribution is about talking about 3D dynamic scene graph, which we believe is a good representation to go from metric semantic mapping to high-level understanding. So what is a 3D dynamic scene graph? 3D dynamic scene graph is a directed graph in which nodes represent spatial concepts. For example, objects, rooms, buildings. So they are concepts which are grounded in 3D space. Images represent spatio-temporal relation between different concepts. For example, An age between agent I and room J can denote the fact that the agent I, for example, a human, is in room J at time t. Not only this is a directed graph as the one that you can see in the video here, but in this graph there are different layers which correspond to a description of the scene at different level of abstraction. So in layer 1, what you have is a metric semantic mesh, which is exactly the same as the output of Chimera. So what the other layers are doing is essentially abstracting the metric semantic mesh of Chimera at a higher level of abstraction. So for example, layer 2 is capturing objects and agents in the scene. Layer 3 is describing places and structure in the scene, and we'll go back to a precise description of these in the next few slides. Layer 4 is describing the rooms in the scene, and layer 5 is capturing the entire building. So the key insight here is that a dynamic scene graph, being a layer graph, is able to describe the environment at different level of abstraction. Moreover, since it is dynamic, can capture agents and things that are moving over time in the scene. And it is also actionable in the sense that, for example, the graph of places, as we will see in an instant, is something that the robot can use for path planning, for example. And these elements are like, a departure, like are novel with respect to the immediate related work to 3D dynamic scene graph, which is the proposal by Iro Armeni at ICCV 2019, which is a very cool paper and you should check it out. So what I'm going to describe in the next few slides is how to go from visual inertial data to 3D dynamic scene, to a 3D dynamic scene graph. So the goal is to get a 3D dynamic scene graph from a camera and IMU in a very heavily populated environment, like the one that I'm showing here. So there is an indoor environment with several people walking around. And in hindsight, what we are proposing here is a transition from SLAM and from a SLAM algorithm to what we call a spatial perception engine, which is an algorithm which is able to infer the geometry, the semantics, and a hierarchy of high-level spatial concept and their relation. So let me give you like a flavor of the different layers and how we build the different layers in a 3D dynamic scene graph. The first one is metric semantic mesh, and I already mentioned this is essentially the output of Chimera. What we have to do to get to a 3D dynamic scene graph was to build in extra robustness to dynamic elements because we have a bunch of people walking around and we need to be robust to those. So what we do in the VIO, we add an IMU-aided feature tracking, which is making the feature tracking robust to the presence of many elements, many like humans walking around the robot. And we also include a technique that we call dynamic masking, which is essentially about avoiding integrating dynamic objects into the map. Let me show you these in particular. So consider the case in which a human is walking in front of the robot. If you are not careful, we can include the map, the human as part of the map, as you see here at the top. With the proposed dynamic masking, we realize that the human is a dynamic entity, so we should not include it in the static map. And the result is that we can avoid, with the proposed approach, which is the one at the bottom, we avoid getting artifacts into the map, and we have a very nice 3D reconstruction, which is robust to dynamic entities. In layer 2, we capture objects and agents, and let me start by describing what we do for the agents, essentially for the humans. So for the humans, we try to reconstruct two things. We try to reconstruct a dense mesh model of the human, which is something that you see here in red in the video, and we also try to reconstruct the trajectory of the human poses over time. Towards this goal, we use a 3D dense shape reconstruction approach, which is a deep learning-based approach from the group of Kostas Danilidis. And on top of that, we had a robust post-graph optimization approach to robustly track human poses over time. And the result is what you see here. We can have over time a constant reconstruction of a dense mesh of the humans in real time as the robot observes the human walking in front of it. Besides figuring out and tracking humans, we want to detect and localize objects. And here we distinguish objects of a known shape from objects of known shape. For the objects of a known shape, we just use a standard Euclidean clustering and we reconstruct a bounding box for the object. For objects instead with known shape, for which we have a CAD model of the object itself, we use teaser++, which is another previous work from our group and is open source, to register the CAD model to the mesh reconstruction done in Chimera, such that we can get a very good estimate of the pose of the object in 3D. So out of this layer, what we have is an estimation of the location of all objects in the scene and their corresponding location. In layer 3, what we do is to extract a high-level understanding of places and structure. So places are simply obstacle-free location in the environment. In particular, you can think about the places as a skeleton of obstacle-free locations in the map, as the one that is shown here. So in this graph of places, each node corresponds to an obstacle-free location in the map, and there is an edge between node I and node J if I can walk on a straight line from I to J without hitting an obstacle. And this is something that comes pretty much for free from box blocks, and indeed we use the ETH implementation to get this skeleton. Besides getting the places, we also extract the structures in the environment, and structures again are just walls, floor, and ceiling, which is pretty easy to do using the metric semantic mesh. Moving to the layer 4, the layer 4 is describing the rooms in a building. I will not go into the details of how we do that, but here what we do is to combine the knowledge of a Euclidean sign distance function that we get from box blocks with the graph of places. And we propose a graph clustering algorithm, which is clustering the places into different rooms, and is also capturing the connectivity between two different rooms, capturing if two rooms are adjacent to each other. One thing that is very important here is that I remarked that in a dynamic scene graph, traversability is described at different level of abstraction. So the mesh is, of course, describing if you can get from point A to point B without hitting obstacles. The same information about traversability is described by the graph of places, and also is described by the graph of different rooms, by the connectivity among the different rooms. This redundancy is a feature rather than a bug, and indeed is something that we believe can really enable hierarchical path planning. For example, depending on the computational resources that you have on your robot, maybe the robot can prefer to get a rough path by planning at the level of rooms, for which can be very fast to obtain a plan, or can try to get a more expensive but more accurate plan at the level of the metric semantic mesh. Finally, the last layer is the layer of buildings. We have been doing mostly experiments in a single building, so it is trivial to get a single node building at the top of the hierarchy here, which is including all the rooms in the building itself. So instead, I will take advantage of this slide to give you a final snapshot of a dynamic scene graph. So here you can probably see the edges and the graph nature of the scene graph, and you can definitely see the different layers which are included in a scene graph. And if you keep playing the video, you can also zoom in on the layer of objects and humans, and you can realize that, first of all, we have a very rich description of the location and pose of objects, but we also describe trajectories of humans over time, which is a pretty unique feature, and we're pretty excited about it. So I will conclude with a simple message here. The simple message is that despite the large amount of research, there is still a large gap that separates robot and human perception. And as a community, we need to go beyond SLAM and start to think about real-time 3D high-level understanding. In this presentation, I talked about two contributions which are going in this direction. The first one is Chimera, which is a real-time metric semantic visual inertial SLAM library, which is modular, so you can use the DIO, the SLAM, the mapping, or the semantic component if you want, and it is also open source for you to use. The second contribution is 3D dynamic scene graph, which we believe is the right representation. It's an expressive and general representation for robot perception, and we believe is the right way to bridge robot perception to human perception. Of course, these are our first two steps. There are a bunch of open questions, and there is plenty of research to do in this direction. One trivial question is to say, we have been showing a proof of concept on how to build a 3D dynamic scene graph using visual inertial data, but of course it's possible to use other sensor combination, maybe multiple robots to build a 3D dynamic scene graph. The second point is that we would ideally like to have a tightly coupled metric semantic SLAM pipeline. So right now, Chimera is mostly annotating a 3D mesh with semantic labels, but is not leveraging the semantic information to improve the 3D mesh itself. There is a general question which is always present in SLAM, which is the question of robustness. How can we make this algorithm as robust or more robust than human perception? And of course, there is one last question, which is about how can we fit learning in the picture. We are using deep learning for the semantic segmentation in Chimera, but there are opportunities also to include learning in the construction and in the structure itself of a dynamic scene graph. So we'll finish here. I will thank our sponsor for supporting this research, including the Army Research Lab, MIT Lincoln Lab, Amazon Robotics, ONR, and Google. And I will thank you all for your attention.